Good afternoon. So in the last lecture, we have started the unit number 6, that is the beam, uh, that is design of beam, and we have covered some theoretical part, and we have covered also the procedure for the design of laterally supported beam. So we have seen that procedure, and we have written step by step procedure for all the types of beams. It means simply supported beam carries a central point load. If simply supported beam is there, carries a UDL and combination of UDL plus point load. So for that, all the types of loading, we have seen the procedure. So today we will see the actual examples based on the design of laterally supported beam. Okay, so we will see the example. So topic is a design of beams. So example number 1. So everyone please write down. A simply supported beam, a simply supported beam, of 5-meter span, of 5-meter span carries a UDL, of 40 kilonewton per meter, carries a UDL of 40 kilonewton per meter, and a central point load, and a central point load of 50 kilonewton, central point load of 50 kilonewton. Full stop. The beam is laterally supported. The beam is laterally supported. The beam is laterally supported. Full stop. Design the section for shear and deflection. Design the section for shear and deflection. It means we have to take the check for shear and deflection. So see the example. Read once again. A simply supported beam of a 5-meter span carries a UDL of 40 kilonewton per meter and a central point load of 50 kilonewton. The beam is laterally supported. Full stop. Design the section for shear and deflection. So this is the problem statement. Now we have to design this beam. Okay, so we will go step by step. Before that, on the basis of the problem statement, we will draw the sketch. The beam is a simply supported beam having a span of 5 meter. Please read the problem statement. Then on this 5-meter span, a UDL 40 kilonewton meter is there. A UDL 40 kilonewton meter is there. That UDL is 40 kilonewton per meter. Again, a central point load is also there. So central point load is there. So central point load is a 50 kilonewton. So it means we have seen 3 cases. So which is this case out of 3? See the procedure, 3 cases we have seen. Please see
Combine of central point load and
and
UDL.
UDL. So it means third case is there. So first case is only of point load, second case is only of UDL, and third case is a combination of both. So we have taken here example combination. It means if we uh, see the case 1 is of central point load only, case 2 is of UDL only, and case 3 is a combination of these two. So we will solve combination of these two. It means you will get both in one case. Okay, so that's why I have taken this example. So this is the sketch, or this is the figure from the problem statement. So now follow these steps. Step 1, follow the steps for design of beam. Okay, what is step 1? Step 1 is
Calculate factor load, maximum bending moment, and shear force.
good. Calculate factored load, comma, maximum bending moment, and maximum shear force. For a given loading, whatever loading is given, for that we have to calculate this for a given loading. Okay, so now calculate factored load first. So factored load is equal to WD is equal to, now here the load will be the different for beam, for point load and for kilonewton, UDL. So for the point load, the factored load will be 1.5 into
50.
here. So here we will write first WD for here for if UDL plus point load, like this we will write. Actually this load will be different because point load and UDL ची addition आपण करू शकतो का, because point load is in kilonewton and UDL is in
kilonewton per meter.
So only we will write here, we cannot add this. So for UDL 1.5 into how much, 40, plus point load 1.5 into 50. So this is how much, 60 kilonewton meter, and this will be 75 kilonewton, correct? So we will keep as it is because we cannot add this. We have to use this 60 kilonewton per meter as it is, and we have to use 75 kilonewton as it is. So only we will, or you can factor this separately. त्याची कॉम्बिनेशन न करता आपण डायरेक्टली फॅक्टर करू शकतो, बट सेपरेटली, कारण का ह्याची ऍडिशन होऊ शकत नाही बिकॉज दिस इज 60 किलोन्यूटन पर मीटर अँड दिस इज अ 75. सो कीप ॲज इट इज. त्यामध्ये हे असंही लिहू शकत नाही आपण डब्ल्यूडी एकदा युडीएल साठी काढायचा आणि एकदा डब्ल्यूडी आपण पॉइंट लोड साठी काढायचा. सो लाईक वी कॅन राईट. So the factored load for point load, it will be the 75 kilonewton, and factored load for UDL, it will be the 60 kilonewton per meter. Got it, everyone? This?
Yes, sir.
So now then we have to calculate maximum bending moment. So here we can add because bending moment having same unit. So now maximum bending moment, that is MD is equal to it now for UDL plus point load. So for UDL, so how much, what is the formula for calculation of maximum bending moment?
WDL square upon 8.
WDL square by 8. This is for UDL, and for point load, what is formula? WD
WDL upon 4.
WDL by 4. So now put this value WD for UDL, where we have calculated here. So how much WD for UDL? How much value?
60.
60. And WD for point load?
75.
75. So here 60 into L is a 5 meter, correct? Divided by 8 plus WD for point load will be 75 into L is 5 meter divided by 4. So add this and this will be in kilonewton meter. So maximum bending moment will be addition of this. How much?
281.25.
281.25 kilonewton meter is the maximum bending. Now we have to calculate the maximum shear force. Maximum shear force. So maximum shear force is nothing but VD. So VD is again for UDL and for point load. So what is the shear force for if the loading is uniformly distributed and simply supported beam is there? What is the formula for shear force?
WD into L divided by 2.
WDL by 2 plus for point load?
P by 2.
P by 2, it means WD by 2, correct? Okay, so WD is again here 60 into 5 by 2 plus WD is here again 75 by 2. So now tell me, this is in kilonewton VD. How much?
187.5.
187.5 kilonewton is a maximum shear force. So here in the step 1 we have calculated the maximum factored load, maximum bending moment, and maximum shear force. So these three terms we have calculated in step number 1 for the given loading. So loading, which type of loading is given? Two types of load given on the beam. So one is a uniformly distributed load, and second is a concentrated load at load that is point load at a center. So the combination of two load is given here. So this is the our step 1. Or have you written?
Yes, sir.
So shall I go next?
Yes, sir.
Okay, so step 2. Step 2. So now what is step 2? Step 2 is the calculate
Plastic section modulus
plastic
required.
section modulus required. Plastic section modulus required. So plastic section modulus is nothing but ZP. So ZP required. So ZP required is equal to MD into gamma M naught divided by Fy. So MD we have calculated. So how much MD value is there? So MD is 281.25. 281.25. So this is in kilonewton meter. Unit of this MD is
kilonewton.
so now here gamma and Fy, these two are in Fy is in Newton per mm square. So we have to convert this kilonewton meter into so kilonewton meter. So conversion जेवढे आपण करतो Newton per mm square or Newton mm. So it we have to multiply by 10 raised to 6. Why? Kilonewton 10 raised to 3 and meter 10 raised to 3. So here 10 raised to 3, 10 raised to 3, we have to multiply by 10 raised to 6 for the Newton mm. Okay. So then gamma m naught, how much value of gamma m naught is? 1.1 and Fy is 250. So tell me how much ZP required?
1.23 into 10 raised to 6.
1.23 into 10 raised to 6. So what is unit for the ZP? Section modulus.
mm.
Section modulus mm. Then
cube.
cube. So please concentrate on the units because moment of inertia having unit is raised to 4. ZP having unit is a cube. Please concentrate units on such units, and that units also you will be see in the steel table also. In the steel table, all the parameters have given. Ag given, thickness of flange is given, moment of inertia is given, radius of gyration is given, then this section modulus is given. So all the properties are given in the steel table and their units have given. If you don't know the unit, you can go on the steel table, then you will be know what is the unit for this particular. Are you getting? Okay. So now after ZP required, what we have to calculate as per the design procedure?
ZD required.
ZE required we have to calculate. So ZE required we have to calculate from ZP. So ZE required is equal to ZP required divided by what?
1.14.
So 1.14. This is the value of what is this value? This value is a shape factor of I section. It means you are going to use I section. This 1.4 you are using, it means you are going to use I section. If in example they have told use another section, at that time you cannot use this 1.14 value. But generally 99% we are using I section for the beams and columns. For columns channel also we are using, but 99% we are using a I section for beams. So here 1.14 we have divided. Are you getting this? Why 1.14? Because this is the shape factor for I section. If other section you are using, you cannot use this 1.14. So you have to use particular shape factor of that particular section. So this keep into mind. Okay. So now 1.23 into 10 raised to 6 divided by what? 1.14. So how much this?
1.078 into 10 raised to 6.
1.078
078.
into 10 raised to 6. But actually this, in this unit, the value will not be available. So convert this into centimeter cube. Can you convert this? This is the cube, correct? So convert this into centimeter cube. Who will convert correct? Who will calculate this? So 1 centimeter cube is equal to how much cube?
1000.
1000. So 1 centimeter is equal to 10 square So 1 centimeter square is equal to sorry, here, sorry, this is 10 this is 10 square, so this is 10 cube, correct? So 10 cube ने divide केले तर किती येईल? So 1.078 into 10 raised to 3 centimeter cube, correct? If you keep as it is, there is no problem, but we have to convert this. Okay. So 10 raised to 3 here, less we have to see the section. Okay. So now have you written this? Okay.
Yes,
So
sir.
now we have to go in the steel table. So select suitable I section from steel table. Write down this sentence: suitable I section from steel table matching the value of ZE required with ZXX. So now the ZXX value, we have to find the value which is matching ZE required. So now go to steel table, everyone please. So which section we have to select here? See, we have to select which section? I section or channel section or other?
I section.
I section we have to select. So the value having I section is a 1.078, correct? Into 10 raised to 6. It means 1.078 into 10 raised to 3. It means 1078, correct? This value we have to find.
Yes, sir.
1078 centimeter cube. Are you getting, everyone? This is our calculated value. So from this calculated value we have to find the value. So I think this value we have to find out, 1078. So see, where is this value? For which section this value is there? Sorry, for this we have to find. So 1078. So find the section. Please find the value. Which value required? 107, more than 1078. So generally use ISMB section or ISLB section. ISMB generally use. See, if you see here, so these are the ISMB section. So generally use this ISMB. So in this range of ISMB, on the next page you can see here you can see ISMB. Here's ISMB sections are there. So which value we have to use? More than 1078, correct?
Yes, sir.
So which value will be more than 1078?
1350.7.
1350.7. You can use this also, there is no problem. So this value ISLB 450 you can use, there is no problem. But generally if we use the ISMB sections for beams, it will be better. Medium beams are there and ISLB are the light beams are there. ISLB is nothing but Indian standard light beam, and ISMB is nothing but Indian standard medium beam, and ISHB is nothing but Indian standard heavy beam. So ISHB we have to use for column. If we have to design the column, at that time ISHB we have to use. If you are using, if you we are designing the beams, at that time use ISLB or ISMB. So here we will use this IS, just a minute. So we can use this also. So this section we will use. IS LB. So write down the properties. So section is ISLB 450. Write down. Section is ISLB 450. So how much value ZE, that is ZXX, how much now here? किती आहे value? How much?
1223.8.
8. This is a centimeter cube. It means if you multiply 10 raised to 3, this will be the mm cube. Are you getting? So now again calculate width of flange. This is required. Then thickness of flange is required. So find these values. Here. So these all the values are required. Whatever underline, you can see this underline. So where is width of flange? For go to the back page. Width of flange is there. Thickness of flange is required. Then depth of section, it means 450 mm. This 450 is nothing but depth of section, 450 mm. Thickness of wave is also required. So these parameters write down. Where is ISLB? Here. Here is there. ISLB 450. Here ISLB 450 is there. So now this is the thickness of flange. This is the thickness of wave. This is the D, depth of section. Then this is the width of flange. So tell me, width of flange is how much? Here. Please find these. Don't depend on me. As I told you, you have to select, you have to take the xerox of this. So this xerox with you. जर ती तुमच्याजवळ नसेल तर तुम्ही स्वतःला फसवताय, मला फसवत नाही. If you are depend on me, you know how to select these properties from the steel table, how to select the section. I will teach, but you have to suffer your whole career. If you are not getting, please ask me, but don't sit blank. Go on the steel table, see the section, find the properties, write down your notebook. I am asking, but you are not responding. So width of flange is here 170 mm. Then thickness of flange is a 13.4. So in this way you have to tell me and write down. So thickness of wave is 8.6 mm. D. So where this required? This required in step number 3. Width of flange, thickness of flange, depth. See the step number 3. What is step number 3? What is step number 3?
Find the suitable eye section.
That is the step number 3. 3 आपण कंबाईन मग डायरेक्टली लिहिलं का मी आता स्टेप सुटेबल सेक्शन. सुटेबल सेक्शन आपण फाइंड आउट करायला लागलोय, म्हणजे स्टेप नंबर 3 न लिहिता डायरेक्टली मी लिहिले का?
No, sir. Classify the section.
हाँ मग तेच
Yes.
मी विचारतोय. Classify the step number 3 is the classify the section. So if we have to classify the section, so what properties are required there? See formulas we have written. There is requirement of width of flange, BF, TF, D. Is this required in step number 3?
Yes, sir.
Yes.
So that I am writing here. माझ्या मनाने मी हे लिहित नाहीये. Why I am writing this only JD, TF, BF, D. So this is required in next step. So that you should know what is requirement from this particular steel table. Okay, so write down this all properties. ISLB 450 section is there. JDE, all the properties write down. Simultaneously, I will also write down. What are these properties? So ISLB 450 section is there. So ZDU value how much? 1223.8 into 10 raised to 3 mm cube, correct? So then width of flange how much? 170 mm. Then thickness of flange is 13.4 mm. Then depth is 450 mm. Then thickness of flange is how much? Sorry, thickness of wave
8.6.
TW. TW is 8.6 mm. So this much are required. So this is ZXX is equal to ZD. Okay. So now from these properties, now again we have to calculate ZE. So this is the ZE available. ZE required is a 1078. 1078 is a ZE required. So now this ZE is a ZE available. Are you getting? This is selected from steel table. It means this is available and this is required. Okay. So now ZE available we got. From ZE available, we have to calculate again ZP. ZP required from again ZE available. So ZP required is equal to again what? S into ZE available. So yes, same factor is 1.14 into ZE available is again 1223.8 into 10 raised to 3. So how much ZP required again?
— 1.395 into 10 raised to 6.
1.395 into 10 raised to 6. So now afterwards this ZP we have to use in the particular formulas. इथून पुढे हा ZP आपल्याला फाइंड यूज करायचा. So this ZP is for ZE available. Whatever section ISLB 450 we have used for this section, ZE available value is this 1223.8, and for this ZE we have calculated ZP value. Okay, so now this ZP value we have to use henceforth. Okay, so have you written this?
Yes.
So now go to the next step number 3. Step 3. What is step 3?
Classify the section.
Classify the section. Okay, so classification is for flange and for wave. So for
Wave.
flange, So for flange, BF by 2 divided by TF is equal to, so BF is a 170 by 2 divided by TF is how much? 13.4. So how much this value?
6.34.
6.34. So now for this value, so what is the classification as per our procedure? See the procedure as I told you. So very, very important this step, because many more MCQ will be asked on this particular step number 3. So these values are very important. For plastic, how much value is there? For compact, how much value will be there? For semi compact, slender. So these values are very important for flange and wave. How much? So this 6.34 value is under which classification?
Plastic.
So it is, don't tell me plastic, tell me the value. Value is very important.
9.4.
So this, for this 9.4, your classification is plastic. So it means your BF by 2 divided by TF, this value or this calculation is less than 9.4. Are you getting? It means your section is a plastic. So after 9.4, next value will be for compact classification.
10.5.
Then after that
15.
15, and greater than 15 it will be slender. So plastic, compact, semi-compact and slender, and for that 9.4, 10.5, 15 and 15, greater than 15. So these values you have to keep in mind for the flange and wave. Okay, so for flange, so classification for wave now. Flange is 4. So D divided by TW. So D is a 450 divided by TW is a how much? 8.6. So how much this?
52.32.
52.32. It means it is less than or equal to, see the classification for wave,
84.
84. It means which classification is there?
Plastic.
Plastic. Okay, you are designing beam. If this is plastic and this is compact, then what will happen? Which you will use? So here generally beam will fail in which element? Your beam will fail due to, in which element? You have seen modes of failure, 3 modes of failure: deflection, then 3 modes of failure of beam: deflection, then
Web creeping.
and then
Web buckling.
it means what? It means what? Your beam will fail in flange first or wave? Your beam will fail due to in the wave buckling or wave crippling. So failure in wave. So you have to consider this. If this will be changed, हे दोन्ही जर चेंज असतील तर कोणतं कन्सिडर करायचं? कोणतं classification you will consider? Wave. Why? Because beam will be failed due to wave. In the wave buckling and wave crippling, these are the modes of failure. So the beam will fail in wave, not in flange. So you have to consider the classification of wave. So here both classifications are plastic, there is no problem. But if they both are changed, at that time you have to use which classification?
For web.
for wave. Why that you understood?
Yes, sir.
Because this is very important, because your beam will fail in wave buckling or wave crimping, so wave will be failed, so we have to consider the classification of wave. Okay, so this is the step number 3. Now we have to move towards step number 4. So step number 4 is a design of
Shear strength.
shear strength. Design of shear strength for resistance. Okay, so shear strength for resistance, that is nothing but VDR. So VDR is equal to Fy into AW divided by under root of 3 gamma m naught. So what is AW? AW is equal to TW into H. So here, what is H? This H or D here? Please see, I am writing here. H and D is nothing but the depth of section. So this value will be H. Are you getting, everyone? This ISLB 450, ISLB 300, ISLB 500, ISLB 400. So whatever this 400, 300, 350, 450, 500 value will be there, this value will be H or D. We are calling H or D. Are you getting, everyone?
Yes, sir.
So here H, TW is 8.6 and H will be, now how much H value?
450.
So how much this area? AW, area of wave. Area of wave. AW is nothing but area of wave. So how much this calculation?
3,870.
3,870. 3870. So now calculate VDR. So VDR is equal to Fy is 250 into 3870 divided by under root of 3 into gamma m naught is 1.1. So how much VDR? Tell me in kilonewton.
507.
0.80.
0.80.
507.80
Yes, sir.
in kilonewton.
Yes, sir.
507.80 kilonewton. Okay, so this is the VDR. So now we have to check for VDR. So check for shear. So what is check for shear? VDR should be
Greater than
than VD. So VDR is a 507.80 kilonewton and VD will be how much VD? I think 187.
Yes, sir.
187.5
5.
kilonewton. It means safe. This is safe. And second condition is VD should be less than 0.6 VDR. These are the two checks we have to take. So VD is 187.5. It should be less than 0.6 into 507.80. So how much this value? 0.6 into 507.
302.68.
30.
4.68.
So I think this is safe, correct? So all the values are satisfied. So hence safe. Whatever section we have provided is safe because VD is 187, so less than this value will be the less than VDR. Again, this next check is there, this check also satisfies. So hence whatever section provided is the same. Are you getting?
Yes, sir.
So now go to the step number 5. So what is step 5? Design
Bending moment registered by section.
design the bending moment registered by the section. Okay, so is nothing but okay. So this bending moment registered by section we have to calculate on the basis of what? Please see the procedure. On the basis of classification of section. So which is the classification of section? As per step number 3, we have analyzed step number 3. So in step number 3, which classification is there?
Plastic.
So for plastic, classification, what is the formula for MDR?
Beta B into ZP into Fy upon gamma m naught.
Into Fy upon gamma m naught. So now beta B. So for plastic section, how much value of beta B?
1.
1. So 1 into ZP. So how much value of ZP? In step number 2, we have calculated value of ZP.
1.23 into 10 raised to 6.
No. This is the calculated value earlier, initially calculated value. We have to require the value last. At the last, we have calculated the value of ZP.
1.395 into 10 raised to 6.
1.395. लक्षात ठेवा ही गोष्टी, वेअर दिस इज व्हेरी इम्पॉर्टंट. जो सेक्शन आपण ISLB यूज केला 450, फॉर दिस ISLB 450 we have calculated this value. Earlier is a ZP required and now this is the ZP. This is the ZP available. कशामुळे अवेलेबल झाली? जो सेक्शन आपण यूज केला फॉर दॅट सेक्शन whatever ZP available that we have written here into Fy is a 250 divided by gamma m naught is a 1.1. So how much MDR? How much MDR?
317.04 into 10 raised to 6.
How much?
7.04.
317.04 kilonewton meter.
Yes, sir.
Correct. So now what is the check for bending moment? So check for bending moment is MDR should be greater than MD. So MDR is a 317.04 and MD is a 281 point how much?
281.25.
25. It means this is MDR is greater than the MD, hence whatever section we have provided is safe. See the procedure. As per procedure, the check for BM is a MDR should be greater than MD, and MDR here we have calculated MDR is a 317 and whatever MD is there, that is 281. It means whatever MDR we have calculated is a greater than the MD, hence provided section is a safe. Got it?
Yes, sir.
Okay. So have you written this?
Yes, sir.
Okay. So we'll move next. Step number 6. So what is step number 6?
Check for design of beam.
Check for design of beam. It means there are 3 modes of failure. The modes will be deflection, then wave crippling and wave buckling. So due to this, beam will fail. So whether this whatever provided section is safe for this particular wave crippling, wave buckling and deflection, that we have to check here. Okay. Okay. So now, so what is first check? First check is a deflection limit, correct? So what is deflection limit? Delta actually is, it should be less than delta allowable. Okay. So how to calculate delta actual for the given loading? What is the maximum deflection for the central point load and what is the maximum deflection for the UDL?
WL cube upon 48 EI for central point load.
WL cube upon 48 EI is for central point load plus, because here 2 loadings are there. Are you getting?
5 WL raised to 4 upon 384 EI.
5 WL raised to 4 upon 384 EI. Okay. So now here moment of inertia we have to take. So that moment of inertia we have to again take, we have to take from the steel table. That moment of inertia is, we have to write here. So this IZZ we have to take. That IZZ value is 2753 into 10 raised to 4 mm raised to 4. This value 27536. You can search also from the steel table. 27536.1 into 10 raised to 4. Moment of inertia. Okay. One more thing here I have to tell you. While calculating the actual deflection or delta actual, so here you have to use service or working load. फॅक्टर्ड लोड घ्यायचा नाही. डिफ्लेक्शन, ऍक्च्युअल डिफ्लेक्शन कॅल्क्युलेट करत असताना फॅक्टर्ड लोड घ्यायचा नाही. सो विच लोड वी हॅव टू टेक? सर्व्हिस लोड और वर्किंग लोड. सो हियर, so WL cube. So how much W for point load? This is for point load and this is for UDL. Are you getting? So 50 into, so now 50 is in kilonewton. So 50 into 10 raised to 3 is in Newton, correct?
Yes, sir.
Into
Yes.
L cube. L, how much L? 5
5.
meter. So 5 meter, it means 5000 mm, correct? 5000 cube.
Yes, sir.
Then 48 into EI. E is the Young's modulus, modulus of elasticity. So for steel, how much Young's modulus? How much value of Young's modulus? 2 into 10 raised to 5. Are you getting value of E? Are you getting?
Yes, sir.
2 into 10 raised to 5. Now I value is a 27. How much? 27 I have written now here. 27,536. 536.1 into 10 raised to 4 in mm. This is one calculation. Then second calculation. 5 by 384 into W. Here W for UDL
40.
40 into L raised to 4. L is a 5000 into 10 raised to 4. So divided by E again 2 into 10 raised to 5 into I is again 27536.1 into 10 raised to 4. How much this calculation?
Sir?
8.27.
How much? 8 point?
27.
8 point? I'm not getting your voice.
27.
8.27
27.
mm. Deflection is in mm. Yeah, please others do the calculations. Is this correct?
Yes, sir.
So 8.27. So now again we have to calculate delta allowable. So what is the formula for delta allowable?
L upon 300.
So L is a 5000 divided by 3000. So how much?
$16.66.
16.66 mm. 16.66 mm. Now see this. Delta actual is less than delta allowable. Whether delta actual is less than delta allowable. It means 8.27 is less than 13.66. It means whatever load coming on the beam, for this load delta actual 50 kilonewton point load and 40 kilonewton per meter UDL, the delta actual will be 8.27. But how much permissible or allowable? Allow किती आहे? As per this formula L by 366, so 16.66. It means whether the provided section is safe.
Yes, sir.
So hence safe. So it means the first mode of failure is safe. There is no failure due to deflection. This is the first mode of failure. Got it, everyone? This?
Yes, sir.
Okay. So now, next strength we will calculate. How much strength will be carrying in the crippling and buckling. Okay. So second is a wave crippling, correct? So that is FWC, strength due to wave crippling. So what is formula for wave crippling? What is formula for wave
B1
crippling?
plus 2N1 into TW into Fy upon gamma m naught.
B1 plus 2N1 into TW into Fy divided by gamma M1. Okay. So what is B1?
Width of flange.
So how much? It is a 170, correct? Width of flange. 2 into N1. How to calculate N1 here?
2 into 2.5 into TF.
TF. So how much TF? Thickness of flange.
13.4.
13.4 into TW. How much TW?
8.6.
8.6 into Fy is 250 divided by gamma m. So how much this value? How much?
594.80 into 10 raised to 3.
594.80 into 10 raised to 3, it means it is kilonewton. Okay, so this much force carried by the for the wave crippling. एवढा force जेव्हा येईल
0.218.
18 or 81 80 18. Okay, and this should be greater than your MD. Please write down. This is written in our procedure. Wave crippling.
No, sir.
So write down there. This FWC should be greater than MD. So how much MD is there? I think 281.25 kilonewton meter. I think this is a strength. Kilonewton meter unit काय येते याचं? नाही मीटर येत नाही, strength आहे. It is strength. So this should be just wait something. Wait. How much total force coming on the member? total force. This is not greater than MD. Please. This should be greater than WD. This should be greater than WD. So WD, how much? WD is, I think, due to shear force. How much WD for due to shear force?
75 kilonewton.
75 kilonewton. Okay, plus due to UDL 40 into 5. How much 40 into 5? It means 40 is a kilonewton per meter is the intensity into span न multiply केलं तर आपल्याला काय मिळेल? ही व्हॅल्यू किलोमीटर मध्ये मिळेल ना? So how much this?
200.
200. So total W is in kilonewton how much?
275.
So this please correct this. This is the WD, not MD. This is WD. So here WD will be 275 kilonewton. So is this greater than this? Hands safe. Are you getting everyone?
Yes, sir.
म्हणजे वेब क्रिपलिंग होत असताना how much load will be coming? So 594. So 594 kilonewton load will be coming while your wave failure due to wave crippling. So this much load will be carried at the time of wave crippling. But actual how much load is coming on the member? Hmm.
275.
So 275 will be coming and carried by 594. So it means our member will be safe for wave crippling. Are you getting? एवढा कॅरी करू शकतोय आणि येतोय इतकाच 275 येतोय बट वेब क्रिपलिंग न फेल्युअर व्हायचं असेल तर किती कॅरी केला जातोय इतका एवढा आला तरच फेल होते पण ऍक्च्युली 275 येतोय इट मीन्स वॉट एव्हर load is coming, this is safe for the wave crippling. Got it? Next is the wave buckling.
WD for UDL म्हणल्यानंतर सेफ्टी फॅक्टरनी मल्टिप्लाय करायचं राहिलं ना 1.5.
Okay, if we multiply 1.5, how much it will become?
300.
300. So this is your service load. So 1.5 is a factor of safety. So ह्याला जरी आपण 1.5 ने मल्टिप्लाय केलं तरी पण 300 किलोमीटर येते. $300 येतो का जास्त येतोय? 275 into 1.5.
नो सर WD आपण शेअर फोर्सचा घेतला ना तो 1.5 into 50 केल्यानंतर 75 आलं.
हा हे 60
तिथं
घ्या 60 हा
तिथं.
इथे चुकलंय आपलं आहे की नाही बरोबर आहे. So here so how much this? Now tell me. 60 into 5 how much?
300.
300. So now this is 375. Now this is correct. So this is greater than 574. So it means hence safe. Now wave buckling. F WB. So what is formula for wave buckling? FWB is equal to
B1 plus 2N1 into TW into FCD.
B1 plus 2N1 into TW into FCD. Okay, so B1 is a again 170 plus 2 into N1. N1 is how much?
D by 2.
D by 2 means 450 by 2 into TW is a thickness of wave. 8.6, no,
Yes, sir.
into FCD. So now we have to calculate FCD first here. Okay. So we will calculate FCD first. So how to calculate FCD? So before calculation of FCD, we have to calculate slenderness ratio. So slenderness ratio is equal to KL by R minimum. That is, how to calculate this value? How this is given in the your design procedure. This formula is given, no? How to calculate slenderness ratio, that is given in procedure. Please speak. Have you written procedure?
Yes, sir.
So this formula is given, or other any other formula is given?
No, sir. This formula not given.
So other formula is given. That formula is 2.425, correct?
Yes, sir.
Into D into TW. So this formula, so 2.425 into D is 450 divided T is 8.6. So how much this value? How much?
126.88. 6.88.
120.88. This is the slenderness ratio. Now for the slenderness ratio, you have to calculate. This is nothing but lambda. Now you have to go to buckling class C. You have to see. So for buckling class C, table number 9C, page number 40, to find this value. So lambda value. So lambda is equal to 126.88. So lambda 1 is 120 and lambda 2 is 130. So here FCD we have to find out. So how much FCD 1 and FCD 2? So tell me, I will not go on the steel table. You have to see this in steel table. Page number, sorry, in IS code, sorry. In IS code, page number 42, table number 9C, for buckling class C, you have to find these values. And for this, we will calculate the FCD value. So FCD is equal to FCD 1 minus lambda 1 divided by lambda 2 minus lambda 1 into FCD 1 minus FCD 2. So write down this first. What is FCD 1 and FCD 2? Tell me from the table number 9C, page number 42. Who will find fast? Many times we have find this. I think we have seen 2, 3, 4, 3. I think 3, 4 example we have seen in the unit number 4. So now find this, and then we will proceed.
$83.7 FCD1.
FCD1 will be 83.7
7
and
74.3.
74.3. Okay. So as per the formula, put this value and find the value of FCD. Follow the formula. FCD1 is 83.7 minus lambda minus lambda 1. Lambda is 126.88 minus 120 divided by 130 minus 120 into FCD1. FCD1 is 83.7 minus 74.3. So how much value of FCD? 77 point. $23. Uday. Other please. Is this correct? 77.
77.233.
Correct. Okay. 77.23. Okay. So now put this FCD value in the formula of buckling strength. So buckling strength FWB is equal to, we have written the formula. So in this particular formula you can write. So here we have written FWD is equal to 170 plus 2 into this. So put the here this FCD value and calculate the strength. So now FWB is equal to much 170 plus 2 into 450 by 2 into TW is 8.6 into FCD is 77.27. So how much kilonewton?
299.06 kilonewton.
299.06 kilonewton. So now this buckling strength should be, just a minute. It should be greater than VD. Why? Because your reaction will be this VD. So this both will be the equal, then bending will be there. So VD. So how much VD is there?
187.5.
187 point. It is 187.5 kilonewton. So hence safe. Actually VD is 187.5, and whatever we have calculated load in kilonewton, that is how much total load? So if this is the your point load and this is, so total load W, if we calculate, so this is 50, this is 40, so 50 plus this 40 into 5,
250.
250. So 250 into 1.5, so it will be
375.
375. See, this is the your so 375 by 2, how much? Because this is reaction.
187.5.
187.5. So correct. So this is greater than, म्हणजे जी रिएक्शन आहे त्या रिएक्शनला म्हणजे बकलिंग कसं होत आहे? So like this, if these two are equal, so 299 load will be the carried, but actual load will be the coming 187 for this particular reactions. So this is the your VD. So this will be the again safe. Are you getting, everyone?
Yes, sir.
Okay. So in this way we can design the beam. Got it, everyone? I think so easy. This is the so easy procedure for design of beam. Okay. So write down next example. Example number 2. Example number 2. So I will give these two examples for homework to you. You can solve this because these are the so easy examples. Okay. So write down example number 2. This is for homework. A simply supported beam. A simply supported beam simply supported beam of effective span 4 meter, effective span 4 meter, carries a factored carries a factored load A simply supported beam of a effective span 4 meter carries a factored load of 350 kilonewton at the midspan. At the midspan, full stop. The section is a laterally supported. The section is a laterally supported throughout the span. Full stop. Design cross section using I section. Design cross section using I section. So this is one example for the homework, and one more example I will give for the homework. That is example number 3. Write down. Check whether ISMB 250 is suitable or not. ISMB 250 is suitable or not as a simply supported beam over effective span of 6 meter, full stop. It carries UDL of 15 kilonewton per meter, including self weight, full stop. Properties of section ISMB 250 are are zxx is equal to 410 into 10 raised to 3 cube, comma bf is equal to 125 comma tf is equal to 12.5 comma tw is equal to 6.9 comma ixx is equal to 5731.6 into 10 raised to 4 raised to 4 comma I think this is the sufficient. So as they have step 2 they have given, so we have to use from the ZP value this section we have to select whether this section is suitable or not, that we have to tell. It means this is suitable, this is for suitable, it means check for deflection, check for wave crippling and check for wave buckling, either these are the safe or not, that you have to tell. If safe, then you have to tell this is safe. If not safe, you have to tell not safe. Likewise, you have to solve this. Are you getting? You have to think about the only this section. Whatever 15 kilonewton per meter load is there, for this 15 kilonewton per meter load, this section they have told us this section you can use, and for this section these properties they have given, and for these properties either this section is safe safe or not, that we have to tell. Okay, so here this is the end of unit number 6. Okay, so write down this and solve these 2 examples for homework. Okay, so wait, I will take attendance and then we will close. Before that, your class coordinator will ask something or about one thing. So I will take attendance and then we will discuss.